All right, let us finish this packet and then, hooray, we'll be done. It feels like we've been working in this pink packet in the applications of integration for a while. Oh well, we're almost done. Here we go, just 3 pages, and then hopefully we can get them all done in this video. If not, I'll just split it up and do 2 videos. All right, next example says given f of x equals the integration from -1 to x. So we have a function defined by an integral. Given that this function is defined as such, for what values of x is f decreasing, and then also where is it increasing? Okay, so it gives me the equation for f, and then it asks about increasing and decreasing. Well, I know f would be increasing when f prime is positive. We know that. We also know f would be decreasing when the first derivative of f would be negative. Like, those are our justifications. It didn't say justify, but it could have. I'm surprised it didn't. So we know to answer questions about something increasing or decreasing, we need to look at that something's first derivative and then determine if it's positive or negative. I have f. I somehow need to get to f prime, so I'm going to take a derivative. Right? I need to know, is f prime positive or negative? So to get from f to f prime, I'm going to take a derivative. So here we go. Taking the derivative on the left gives me f prime. Taking the derivative on the right is your second fundamental theorem of calculus, second FTC. When you take the derivative on this left side, it just gives you f prime. When you take the derivative on the right side, it's going to cancel. You just change your t's to x's. So that seemed like it was a little bit weird. That should be an X. Sorry. It seemed like it was going to be weird, but it was actually really nice for our second FTC. It means all I have to do is change those T's to X's. I do not need to worry about a negative because the X is on the top, and I do not need to worry about chain rule because it was just a regular X. The derivative of it is 1. Okay, so that's pretty good. And look, it's already factored for me, so I know the critical points are going to be at -2 and then at 3. Those are the values where you have critical points, where the derivative is 0, and then we just need to test it. That chunk's always positive, so that's really lovely. If we now test that piece, if I pick a number bigger than 3, that chunk will be positive, which means overall it's going to be positive, so f would be increasing. If I pick a number like 0, it's still going to be positive. Since it's an even multiplicity, that factor wasn't going to change. So still positive, therefore still increasing. But now if I pick something like a -10, that chunk will be negative, which means overall it'll be negative. So answering questions about increasing or decreasing, we know we need to do the first derivative sign chart. Second FTC kind of enabled us to get this derivative done pretty quickly. Increasing is when the derivative is positive. If you were to say -2 to infinity, that's fine. I'm going to split it up and say -2 to 3 or the union 3 to infinity. And then for the decreasing, that's just -infinity to the -2. Seems like a weird question, actually is a very straightforward, very easy question. If it just started you with this and asked for increasing, decreasing, almost everyone would get it right. It's already even factored for you. All you have to do is do the sign chart. The fact that it's disguised as this function defined by an integral, you have to take the derivative, so a second FTC kind of sneaks in there. The fact that they add in that extra little conceptual stuff, it doesn't change how hard the math is. You just have to know the conceptual stuff. Okay, next question. Also a little kind of weird one. It says, suppose that 3x² minus 12 equals this integration from c, some constant, up to x. And I'm integrating f of t dt. It says, what is f of x? And you're like, oh, okay, let me think. I have this integration of f of t, and then I have an x up here, so I somehow want this x to change, and I want that x to somehow fill in for the t. But luckily, we know second FTC again, right? Both of these questions, second FTC, they come up in a lot of questions. If I were to take the derivative of this right-handed side, I know the derivative of this integral, those would cancel. I would just take the x and plug it in. So if I take the derivative on the right, that will give me f of x. I know that from the second FTC. But to keep it fair, I'm also going to need to take the derivative of the left. The derivative of that 0, so it doesn't matter. The derivative of this is 6x. There we have it. Taking the derivative of both sides will give you that f of x is 6x, right? I'm going to take 6 and multiply it by the variable. That's what your f function does. Now it says find the value of c. So we're going to take that function and plug it back in. Instead of f of t, right, I know the function f of x, it's 6 times x, so f of t would be 6 times t. And let's just try to integrate it, and let's see what we can do. The left side's still the same for now. If I were to integrate it, it would be 3t squared, and then I would evaluate from c to x, which means the left side is still the same, which means I would have 3x squared minus 3c squared, right? So I integrated, then I plugged in. Look, the 3x squareds are going to cancel, so I have 12 is going to equal, I definitely messed something up, right? It should have been a minus, so then this should have been a minus. This should have been a minus. This should have been a minus. I'm glad I caught it now. Otherwise, I would have had an imaginary answer. That wouldn't have been fun. So it should have been minus 12, minus 12, minus 12. I just miscopied it. My bad. Oops. So it should be a negative 12 equals negative 3c squared. And then the negatives will cancel. That's why I knew it was going to be a problem, because I knew that side was going to be negative. I was like, uh-oh, that's no good. Divide by the 3, so get 4 is equal to c squared. So it looks like here we will get the two answers. A c could either be a positive 2 or it could be a negative 2. It looks like we got the two answers. Now, a little quick way that you could do this, remember, it kind of started like this, right? You had the 3x squared minus 12, and then it equaled that integration. If I just changed the x's all to c's, I would have had 3c squared minus 12 equals the integration from c to c of f of t dt. You know, whatever. That doesn't matter because all of this is going to be 0. So then you'd have 3c squared minus 12 equals 0. 3c squared equals 12. You will get to this same thing. It's kind of a little bit of a shortcut. I've never seen that not work. I'm not going to guarantee that it's always going to work. But I would recommend second FTC. That's how we find the f function. You could always just plug it in, do it the slightly longer way. It's not very hard. Okay, next one. It's just some properties. The rest of this is just some like miscellaneous questions for review. So we're going to burn through these quick because I want to be done with this packet. I want to be done with these videos. So the next couple are just going to be some review questions, and we're going to just power on through them. I guess there'll be a little bit of new stuff at the end, but the next page and a half or so will be review. All right, so it tells me the integration from negative 2 to 5 of f is 4. Then I see that f in 2 to 5. Okay, but I got this 3 and I got the minus 2, so I have 3. Then the integrations of f minus, then I need the integration of 2, right? Don't just subtract the 2. That 2 is a function that must be integrated. So 3, and then we know what all of this is, right? The question tells me all of this is 4, and then minus 2. You can either integrate it, or you can think about the graph. 2 would be a horizontal line from negative 2 to 5, right? That's a rectangle. The height of the rectangle is 2. The width of the rectangle is 7. You really shouldn't need to graph it. Just remember, any constant's a rectangle. The height of the constant is, or the value of the constant is the height, and then b minus a will be the width. So I'm going to get 12 minus 14. So this answer should be negative 2, right? This chunk right here, you can either use the graph to look at the area bounded by the rectangle, or you can just remember, hey, there's the height of the rectangle, b minus a, that's the width. Or if you want to, you could just integrate it, right? That would be 2x, and then you could evaluate it. So then you have 2 times 5 minus 2 times negative 2. Don't forget all of this stuff would be subtracted, and then all of this 10 minus negative 4. So that would be the 14 again, and then you have 12 minus 14. It would still work, right? So this chunk, you could integrate it, or you could think about the graph, find the area of that region geometrically, or you could just know, hey, okay, that's a rectangle, that's the height, b minus a is the width. Either way, remember, you can't just subtract 2. The common mistake would be to tell me that 10 is the answer here, because you would do 3 times the 4. You would try to take this and plug it in. 3 times 4 minus 2. That's a really common mistake. I guarantee you, like if this was answer choice B, I guarantee you this would be one of the other options to try to get you. But that's not the right answer. This has to be integrated. It can't just be subtracted. Okay, next one, we have a piecewise function. Typically these are a lot of work, but not a lot of hard work. So we want to find the area bounded by this graph between negative 3 to 2. Now, typically, they're going to give you functions that are continuous. It doesn't have to be. Even if I had something that was like this, you could still find the area bounded by it. Like, that would be okay. Most of the time they will give us connected continuous functions, but it's not necessary. All you have to do, if I want this integration, I'm going to split it up. We'll go from -3, this transition point here, you can tell is at 0. So from -3 to 0, we'll do one function, and then from 0 all the way to 2, we'll do the next. Okay, so we're going to have to split it up into 2 parts. Find the area bounded by this, between its interval, and then add the integration of the rest of it. And both of those functions are pretty easy, pretty simple polynomials. They're very easy to integrate. Plugging in is going to be simple, right? The problem with the piecewise isn't how hard the work is going to be. It's that I have to do 2, or maybe you'll have a 3-layer piecewise. It's the volume that's a little bit annoying, not the difficulty or the rigor of it. Here we go. 1/2 x squared plus x. That's from -3 to 0. Sometimes I like to do them individually. Sometimes I do them all at once. Most of the time I do it all at once. So we've integrated. Now I'll have the upper evaluation. Plugging in 0 is just going to cancel. So I'll have the lower evaluation. That's going to be 9/2 minus 3. So all of that was the upper evaluation. Then I'm going to have the lower evaluation, or this, that was all the, sorry, not the upper evaluation. This was all the first integral. Plugging in 0 is going to cancel. Plugging in this gives us that. Then over here, plugging in the 2 will give us 8/3 plus 2. Plugging in the 0 will give us 0, right? So that's really nice. We've got a couple chunks that will cancel. This negative, don't forget to distribute. -9/2 plus 3 plus 8/3 plus 2. So we could write this as 5 minus 9/2 plus 8/3. Like, that would be fine for a free response. You don't necessarily have to go farther if you wanted to go all the way to the final singular answer. The common denominator between them all would need to be 6, because that's the least common multiple between 1, 2, and 3. So that would be 30/6 times 3. So that would be, that would be, times 3. So that would be 27/6. So we have a 30/6 minus a 27/6. This we need to multiply by 2 to create the denominator, so that would be also by 2 to keep it balanced. So we're going to have 30 minus 27. That's 3. 3 plus 16. Okay, so that would be 19/6 if you wanted to get it to the final singular fraction answer, which you would have to for a multiple choice. Right, so piecewise functions, you have multiple things to do, but generally both of the parts, or all 3 of the parts, generally they're all going to be pretty easy. Next page. The rate at which water is being pumped into a tank is measured by this function r sub t. A table with selected values of r for the given time interval 0 to 20 is shown below. Great. And it contains 50 gallons of water initially. Awesome. Again, we've seen stuff like this. This is another opportunity for us to remember that the integral of your rate of change is your amount of change. When I integrate the rate, you get the amount of change. I'm not going to bother drawing the pictures. If you want, you can just go ahead and look on the online notes key, right? Or you can just pause the video. I don't want to graph them because I'm a little bit lazy, but we're going to do the left Riemann sum, and then we're going to do the right Riemann sum. Okay, but I'm not gonna graph them because I don't want to. Left Riemann sum, and it says 4 left Riemann sums. So here we go. The area, or I guess we could do the change in the water, would be the integration, which we're going to approximate by doing a Riemann sum. Okay, now let's see. Will I have a universal width? That's going to be 4 for the width. That's going to be 5. You don't even have to bother checking the rest of them. There's no universal width, so we will just have to do each one individually. The width of the first one is 4, and then since it's a left Riemann sum, the height will be 25. Next one, the width is going to be 5, and then you'd be using the 28 for the height. Okay, then the width of this one, let's see, 9 plus 8 would be 17, so the width is going to be 17. You'd be using the 33. And then the last interval is a width of 3, and then you would be using the number on the left, the 42, for the height. Okay, so there we go, a left Riemann sum, very nice. If you were to type this into the calculator, right, we would find that this change in water is going to be about 630 gallons. Now, occasionally you will get questions that will ask, how much water has flown into the tank, right? So this would be your wait, there was, yeah, it's pumped in, right? So that would be your inflow amount. That's how much water has come into the tank over that specific time interval. You want the final amount. That means I have to take my initial and then plus the change, right? So I'm going to take my 50, which was my initial value, plus the 630, and so we know 680 gallons. That's how much water is in the tank at the end of the interval. Sometimes you will get questions that only asks for the change, either how much has come in, or if it was an outflow function, how much has drained out of the tank or has flown out of the tank. Sometimes you will get only questions that ask for the change. But if it wants the final quantity or that final amount, you would either take the initial and add the change to it, or you could take the initial and you could subtract it if it was an outflow. But here we had an inflow, so we took the initial, add the change, bam. Don't forget to add the 50. Next one, we're going to do a trapezoid, same regions. So again, the change in the water is the integration, which we're going to approximate with the Riemann sum. You can always factor out the 1/2, but we do not have the universal width. So here we're just going to have to do each trapezoid individually. No big deal. The width of this one was 4, and then you do base 1 plus base 2. The next one, the width, remember, was 5. Then you'd have the base 1 plus the base 2. And then we'd have the next one. I'm not going to have enough room, will I? The next one would be the width of 8. And then you'd have the base 1 plus the base 2. And then the last one was our width of 3, the base 1 plus the base 2. Guess I could have left it. Oh well. And then you would still just need to type all this into the calculator. You could get that your change in water is going to be about 690.5 gallons. So since we want the final quantity, we would just add the 50 to it, and we would get 740.5 gallons. This is how much has come in. This is the amount in the end, at the end of that interval. Okay, so that's the change. This is the final quantity. You have to think, do I add to the initial or subtract from it? That'll be based on whether the question tells you an inflow or an outflow. Most of the time it seems like stuff is going in, but it could also just as easily have started with 500 gallons and then have been flowing out. I guess it would need to start with like 1,000 because you'd need to have an initial amount bigger than how much is flown out. Otherwise, it wouldn't really make sense. Okay, so let's look at part C. It says a rate function no longer going to be estimated by these data points in the table. Now it just gives me the function, right? So that's my new rate. So it says find the amount of water when time equals 20. Okay, so here we're going to again find the change in water, which for us would be the integration. But now I don't have to approximate it. Right now I don't have to approximate it. Now that I actually have the equation, now I can actually do it. I'm going to use my graphing data calculator, and I'm just going to math 9 that sucker. I'm just going to type it into the calculator, get it to do the integration for me. Now this is equals. It's no longer an approximation. It's equals. I would get 685.099 gallons. That would be exactly how much water comes in. But again, it says the final amount. So I'd add the 50. So I'd get 735.099 gallons. That is exactly how much water is in the tank at the end. Remember, the integration tells me the change. We can approximate that change by doing a Riemann sum, but we're going to get this exact change by actually doing the integral. We couldn't get it exact previously because we didn't know what the function was. We only had data points. But now that I have the model, now I can actually do this. We could integrate this by hand later. We don't know how to integrate the exponentials. We will learn that in the next notes packet. But for now, we could always just math 9 it to get the value, and then of course add the 50 since it wanted the final. That's how much has come in. That's how much I started with. So that's just how much is in there at the end. Okay, speeding through. We got one more page, and then we will be done. And these are going to be more fundamental theorem of calculus questions. So Ftc, integration of the derivative, is going to be from a to b. That's f of b minus f of a. Right, there's your fundamental theorem of calculus. And then you also know, hey, if you want to know your next x value, you start with your previous, or you want to know your next y value, you start with your previous, and you add in the amount of change. right? So you take your initial or your first amount. Can I spell initial? Yep, initial amount plus the change. That would be equal to your final. Ooh, can't spell final. There we go. Final amount. It doesn't have to be final. It could just be the second, and this could be your first, right? It doesn't always have to be at time equals 0, x equals 0. But you take the stuff that you know, you add in how much change there is, and that change could either be positive, which causes your stuff to go up, or it could be negative and cause your stuff to go down. But your fundamental theorem of calculus, if you just arrange it, that second quantity, if you take the first quantity and add in the change, and it has to be the change from what I start with to what I want to end with, right? Initial plus the change is going to give me the final, or that first value plus the change from the first to the second has to be the second value, right? Whatever this number is, if this is a plus, those should always match, and those should always match. If I take the value that I know, and then I add the change from what I know to what I want to know, it will always give you that value you want to know. And how do I get the change? You integrate the rate. Okay, you integrate the derivative. That's what our fundamental theorem of calculus is. Let's apply it. Here we've got this derivative. This is something we couldn't even integrate since it's missing the x. U sub will not work. So this one, we couldn't integrate it. But it says find f of 3 given f of 2. So I know I could set up this function. I could set up this equation. I'm going to use 2 and 3. That's the one I know about. That's the one I want to know about. So 2 to 3. Then I'd have f of 3 minus f of 2. The calculator can do that one for me. I was given this one. This is the one we're trying to solve for, so I'm just going to rearrange it. So I'd have f of 2 plus the integration from 2 to 3. And of course, the thing that you're integrating is the derivative. Okay, you don't necessarily have to even write this. If you want to, you should hopefully be able to just start here. The value you want to know, you just take the value that you do know and then add in the change. And to get the change, you integrate the rate, but you have to integrate the rate from what you know to what you want to know, right? Regular integrations, that's the net change, could go up, could go down, doesn't matter. Integrating the rate is going to give you the amount of change from what I want to know, from what I know to what I want to know. F of 2 was 7. I don't even know what this answer is, but we can just say, hey, this piece, we're going to math 9 with my GDC, with my graphing data calculator. We know this piece is 7, so 7 plus that math 9 could end up getting us that answer, 7.241. But I'm not going to type in the calculator. I already have it written down on my notes key. I guess this would have been the 0.241. Then you have 7 plus the 0.241. There you have it. Fundamental theorem of calculus, pretty good, especially when you can't integrate. Okay, next one. I want f of 4. Let's just start here with this. If I want f of 4, that means I'm going to take f of 5. I'm going to add in the integration from 5 to 4. And of course, the thing that you're going to integrate is the derivative. The fact that this is right to left, it doesn't matter, right? It's still going to work. The negative will be built in to the function. Since this is right to left, when I integrate it, when I do the math 9, this is already going to have the negative built in. This will work. Take the value that you know, add the change from what you know to what you want to know, and as long as those match and those match, if that's a plus, it will work. So then this, we know we could plug in the 1.3. This we could use the graphing data calculator to find, and then if I were to take 1.3 and then add in that integration, it will give you the correct answer, which is 0.907. Okay, if you didn't want to do that, you could have used the fundamental theorem of calculus. You could have integrated f prime from, 4 to 5, which would have been f of 5 minus f of 4. You could set it up this way. We know the calculator can give me this. We know this is given. That's the thing we're going to solve for. So you could rearrange it to solve for this. F of 4, it would be, you'd have to add this piece over, subtract piece back, so those two just swap places. F of 5 minus the integration from 4 to 5. Would this give me the same thing as this? This one's got f of 5, and then this one, this one's plus 5 to 4. This one's minus 4 to 5. If you were to do this, right, let me get a different color really quick. This number right here would be positive, and so if you were to subtract the positive number, There we go, right? That's going to cause it to go down. Subtracting the positive number, there you have it, it'll work. Here, this number, since the order is backwards, this is going to have the negative, right? When you math 9 this, it will be negative, and here you're going to add the negative, right? Adding the negative or subtracting the positive is still going to work. So whether you add the integration from 5 to 4, remember those match. If it's addition, and those match. If it's subtraction, that just means you started off going to right to left, but I flipped it, and then I went left to right. But since I went left to right and I flipped that order, you would just have to, instead of the minus or instead of the plus, you could flip it and change it, right? So you could have gone straight from this to this, right? If you would have flipped that order, you just have to flip the sign. Either way, you should get the same answer. Okay, next one. How are we doing on time? Okay, we're doing okay. A pizza with the temperature of 95 degrees is put into a room to cool. Pizza's temperature is decreasing, so it gives me the rate function. Estimate the pizza's temperature at this time. Okay, so here we go. I know the change in the temperature is going to be the integration of the rate of change. And I want the change in temperature from 0 to 5. So I'm going to integrate from 0 to 5. And then we could math 9 this with my graphing data calculator. And we could get the change as I think it's, oh my gosh, I don't even really remember what it was. I think it's like, I guess we'll have to get it out. It's like 23.608, I think. Yeah, 23.608, I think. I'm pretty sure that's the number. I can't think of it off the top of my head. I just have the final answer written down, but I'm pretty sure that's the right answer. But anyways, that's the change in the temperature, and it says, hey, your temperature is decreasing at this rate. Okay, so I would have to take my 95, and then I would have to subtract, right? This number is going to always give you, like this thing is going to be positive. The negative is right here in the word, right? That's the negative. It's not in the function. It's in the word. So I'd have to take my initial, subtract that positive change. The answer should end up being 71.392. So, about 71 degrees Celsius. I know this is right. I can't remember if that's precise. I'm pretty sure I'm doing the math right in my head. I have this on my answer key, so I know that answer is right. I don't have that number on my answer key, but I'm pretty sure it is 23.608. That's what I remember from last year. But anyways, you could check it by math 9, but I know that's the correct answer. Find the change by integrating the rate, take your initial, and he would subtract the change because of the word decreasing. Okay, one more little concept, and then we will be done. Okay, let me actually pause this really quick, and I'm going to draw a diagram, and then I'm going to unpause it, and it's going to magically be there. Okay, poof, like magic. There it is, right? The wonders of that pausing. Here, we're going to talk about something that we did a while ago, which is net area versus total area. Remember, a regular integration of a regular function, that's net area. The functions could be positive, or it could be negative, based on whether it's above or below. And if we're integrating from left to right, above is positive, below is negative. If you're working right to left, everything would be backwards. Above would be negative, below would be positive, right? We don't usually work right to left, but if you do, everything is reversed just because of that property of definite integrals, where if you flip the order, you flip the sign. Generally, we work left to right, so above, the areas above will accumulate and count as positive area. The region below will accumulate and count as negative. So I know regular functions from regular old integrations sometimes could be above, sometimes they could be below. That's going to be the net area of that function. Now, if I wanted the total area or the gross area or that geometric area, I know I wouldn't want this to count as negative. Instead, what I would want to do is basically find what's this corresponding region up above, and I'd want to just know, hey, like instead of that region being negative, I want the same region, but it to be positive. So I have the size of that one, the size of that one, right? If I just ignored the negative and got all of those things to count as positive, well, that's what the absolute value would do, right? The absolute value would flip that sucker up, and then everything would count as positive. So I know regular integration, that's net area, and then the total area could be found by taking the absolute value first and then integrating. You cannot do the integration and then do the absolute value. That's finding the size of the net area. That doesn't help, because when you do this, the negatives and the positive would cancel out, and then you just be finding the size of the gap or the size of that number that results. You need to take the absolute value before the positives and the negatives cancel. So the absolute value first, and then integrating. That's how you can make sure that nothing counts as negative. It's all above. It all counts as positive. Total area. Now the same thing is going to be applied going back to some kinematics. Remember, we have the position function, the derivative of the position, that's your velocity, right? The rate of change of your position is your velocity. And so if I wanted to integrate the velocity, I'm integrating the rate of change of your position, and we know the integration of the rate is your amount of change. So if this is your rate of distance per time, if you accumulate that over a time interval, it's going to give you the amount of change, the distance that you traveled. But just like how regular integrations are net, absolute integrations are total, the same thing is going to be true to help us out here with this displacement versus the total distance. Regular integrations of the velocity will give us the net distance. This velocity could be positive, could be negative. So if you were integrating, they could cancel out against itself, and then that's going to give you the net change. But for the total distance, I wouldn't want anything to cancel. And if you remember way back when, like if we had a motion that went like this, like to the right, to the left, to the right, I'd have to figure out how far does it go in this interval? Then how far does it go in this little leg of the journey? Then how far? We had to do something that looked like this. Find all the t values, then find all the positions. Let's say 0, 1, 2, 3. We'd find what those numbers were. Then we have to find the change in positions. Let's say that was like a +3, -4, +7. And then what you would do if you added all of those together, counting the negatives as negatives, well, you would get the displacement. But what you'd have to do is if any of them are negative, you would just ignore the negative, right? This is how we did total distance way back when in the first semester. But now that we know integration and we know the fundamental theorem of calculus, we don't have to do this anymore, right? Displacement, you also know, was S of B minus S of A, right? It's just that change in the position. So now that we know integration, the displacement and the total distance, especially the total distance, they become a lot easier. Just like for regular area, the net is the regular function, absolute is the total. Same thing is going to be true for this kinematics application. The net distance, aka the displacement, that's your regular integration of your velocity. If you take the absolute value of the velocity and then you integrate it, that's going to give us our total distance. So integrating the velocity gives me the displacement. Integrating, absolute value of the velocity, that's called the speed. Integrating the speed gives you your total distance. Okay, now let us practice and then we'll be done. I'll try to finish this because I've got a class to teach in about 10 minutes, so we got to go fast. We should not take 10 minutes, hopefully. All right, here we go. Last couple of examples. Here we go. Finding a second position, right? So we're going to have a particle motion question. Finding a second position given the velocity function and an initial condition. Okay, so it says a particle is moving along an x-axis according to this velocity function. It's even factored, so you could see the critical points. So time equals 1, time equals 3, and time equals 6. So it probably looks something like this, right? It probably does something that looks like this. Or maybe it does like left, right, left. Who knows, right? But it's probably this. I know the velocity. And then here it says find the position at time equals 5. So find S of 5. Given that at time equals 1, the particle's at 2. So I know the position at 1 is 2. So I could FOIL all this out, get the polynomial. I could then integrate the polynomial indefinitely, use this condition to solve for c, and then once I had that function complete, then I could plug in 5 no problem, right? That would be our method 1 for doing this. I could multiply it out, use the condition to solve for c, multiply it out, then integrate indefinitely, use the condition to solve for c, and then once I have that completed particular position function, then plugging in 5 would be no problem. But we're not going to do it that way. We're going to use the fundamental theorem of calculus. Okay, so it says find the position at 5. So find this, given this. Let's just go back, right? This idea of the first fundamental theorem of calculus, if I integrate the derivative, that's going to give me my f of b minus f of a. Let's think about it like this. if I integrate s prime, that's going to be s of b minus s of a, right? That's the same thing, except instead of f's, it's s's, right? So it will work for your kinematics questions. But instead of labeling things as s prime, that's the same thing as the velocity. So we know, because of the fundamental theorem of calculus, the integration of the velocity over an interval will give us the displacement, right? So here we go. That works because this is s prime, right? The velocity is s prime. So integrating the velocity gives us the displacement. Okay, so here we go. If I want to know the position at 5 and I know the position at time equals 1, let's check it out. If I want to know at 5, start with 1, then I'm just going to have to add the change from 1 to 5. What I integrate is the rate of change. The rate of change of your position is your velocity. Okay, so finding this second position, all I have to do is take the position that I know that I'm starting with, not necessarily at time equals 0, but that's just the one that you know first of all. Take that thing that you know, add the change from what you know to what you want to know, and how do I get the change? As I integrate the rate. Integrating the velocity gets you that net change, that displacement. Here I was given this, right? You were given this. That's nice. That was, what was it? 2. This I could math 9 with my graphing data calculator. And then since that was 2, this I could get with the calculator. Then I could get the answer pretty easily. And I could get, hey, this position, right? The position at time equals 5, it's negative 10/3. Okay, so if I know one position and I want to know a second position, I could, right? If I really wanted to, I could multiply that out, get the velocity formula, integrate it indefinitely, use the first condition to solve for c, have that particular solution. Once I have the particular solution, plugging in any other second or any other third or any other fourth or fifth or however many other locations you want. Once you have that particular solution, finding the next positions would be easy. You're just plugging it in. But you don't have to do it that way. You can if you want, but you can also utilize the fundamental theorem of calculus. Take the position that you know and then add the change from what you know to what you want to know. Now 1 to 5, that's left to right. Even if this was 1, even if you're working back to 0, it wouldn't matter, right? If this always matches and this always matches and that's a plus, it will always work, regardless of if this makes you go left to right or if it's right to left. This will always have, even if it has the negative built in, the calculator has your back, right? Take the position that you know, add the change from what you know to what you want to know. It will always work. Last one, determine the initial position. So that's the position at time equals 0, given that, I don't know why that's p, that should probably be an s. Given that the position at time equals 6 is 5. So here we go. If I want the position at time equals 0, I could take the position at 6, then I could add the integration from 6 to 0. And of course, what I would be integrating is the velocity. This will work. I guarantee you it will work. If you don't want it to look like that, you could do s of 6 minus the integration from 0 to 6. Both of these would give you the same thing. This we were given. This we could use the graphing data calculator to get. Either way, you could end up getting the same answer, which is 23. Okay, so these kinematic ones kind of tie into your fundamental theorem of calculus also. If you needed to, you could have set it up right here. I know the integration of s prime. The time values that you need would be 0 and 6. So that would be s of 6 minus s of 0. You could rearrange this. That you know the calculator can give you. This is what you're given. This is what you're missing for. If you rearrange it, you would get this. Or if you wanted to, you could have it like this. But those ones, hopefully, we can kind of understand. It's just like the ones we did up at the top, except instead of f prime and then working with f, it's giving you s prime, which is v, and then just having you work with s, right? Fundamental theorem of calculus still tackles all that stuff. Hopefully that makes sense. If not, make sure you ask me about it at some point.